First is Professor Ram Seshadri from the University of California at Santa Barbara. Ram is an expert in inorganic materials, or perhaps I should say inorganic compounds. I'm not sure, having read his abstract. Inorganic something. Ram.
Thank you very much, Andy, and thank you all for being here to listen to me, and thanks so much to His Highness for now, I think, 17 plus years of hosting all of us so generously. I don't think there's any other meeting in the world that I know of where the ruler invites everyone home for dinner after the meeting. It's really a remarkable thing. I also want to acknowledge this is actually my 5th time, and I'm grateful that I continue to be invited. I'm actually particularly pleased that over the last 15 or so years, I think at least about 30 of my group members, students and postdocs, have visited over this time, and I have 2 of my graduate students here. So I'm going to talk about, this is the title, Discovering Compounds and Designing Materials, and I'll try and tell you what I mean by this. So all of us, well, many of us, have this goal of making compounds, particularly those of us who are in the inorganic world. We have this goal of making compounds that use some select elements from the periodic table, and when they are assembled into the right structure and composition of crystalline matter, examples shown here. We just have in this example one organic molecule, that's PCBM, a common molecule used in organic photovoltaics, but the rest are all inorganic. There's a zeolite on the top left, used for catalysis and separations. Photovoltaics, like Osman Bakr spoke about today. Bismuth telluride, this layered compound on the left, is a common material in thermoelectrics, but also topological insulators, and then there are battery cathode materials. But how do we go from this to this? Or in other words, if we know the function we're looking for, how do we know how to assemble the right structure and composition of matter? This is really sort of the leading problem, has been for a long time in materials research. And this was an article that Tony led, and I was brought in for my graphic skills, but Tony has perhaps shown this before previously, but oftentimes it happens that the chemical compound exists on shelves somewhere, made by chemists or material scientists, but the actual functionality is not recognized for a long time. So if you take, for example, something like polyacetylene, it was already sort of, hints of it were already known in the 1860s and 70s, but the actual discovery that Christine Luscombe so beautifully illustrated, the story of the visitor using an excess of bromine or whatever, which was supposed to be catalytic, it became the dopant. And that was, the ChemCom paper was in 1980, and the Nobel Prize was in 2000. And there are many, many other examples here. In fact, one of my favorites is this one here. So that's John Goodenough on the left. So he had already, by the time he did this work, he had already developed lithium cobalt oxide, or he had studied lithium cobalt oxide and related compounds for their for their magnetic properties. In fact, Goodenough had a paper on lithium nickel oxide in 1958. Then in 1980, he recognized that these compounds could be used as battery cathodes. And this was the paper that came out of Oxford at that time. And in the paper, Goodenough actually explains the design principle that they use. And if you read this design principle carefully, and then you start thinking about it, you recognize that there's probably never going to be a better cathode material than this one in terms of just effective functioning. Of course, people are going to look for alternate cathodes because they want to get away from cobalt, etc. But in principle, this is going to be a hard cathode to improve on. Yeah. And this, of course, won the Nobel Prize some years ago in chemistry, along with 2 other people. So we want to find compounds. So it's interesting that Google then publishes a paper that says that they can find, in fact, they don't use the word compound, they find materials, and we'll explain the difference in a minute. They say they found 2.2 million structures, and they said it's an order of magnitude expansion in stable materials known to humanity. So this already, there are lots of problems in the statement. And as a rule, I wouldn't believe statements like this too much because it did appear in nature. But when they say they have an order of magnitude expansion of stable materials, they completely ignore anything other than inorganic compounds. They ignore polymers, they ignore composites, they ignore alloys, they ignore morphs, for example, all of which, you really don't have a limit on the number that are known, polymers particularly. So anyway, this was interesting, but then Tony and I went through the list of compounds and we realized that there are actually problems. This is published in Chemistry of Materials, picked up by the New York Times. For example, if you go through their list, you realize that the novelty in a lot of their predictions has to do with the artificial orderings of chemical elements. For example, if you make a compound with two different rare earth ions, typically an oxide with two different rare earth ions, you never ever have them order on distinct lattice sites. Okay, so La2O3 is an oxide, but you could imagine making LaNdO3, and if the lanthanum and neodymium were ordered, that could be a distinct and new compound, but lanthanum and neodymium would never order in the real world. So Tony and I went through 10 out of 380,000 compounds in their so-called stable structure database, and in every case we found that there was almost a precise analog in the inorganic crystal structure database. So here, for example, is a compound that they claim is new, and here is basically the equivalent compound in the crystal structure database if you don't assume artificial orderings of cations like hafnium and zirconium, which are the two sort of most similar chemical elements in the periodic table. Anyway, so it's still a problem. It's not a solved problem to find new compounds, but also we think a compound is not a material, because as we showed you, chemical compounds exist for a long time before people recognize their material importance. So I'm going to talk a little bit about the discovery of new chemical compounds, and you saw a beautiful talk from Lingling Mao earlier today. It's these halide perovskites and their related halide materials are a huge sort of area of discovery. These are the people implicated, including Dr. Pratap Vishnoi, who's in the audience, and former students and postdocs, and current students and current students. And you've already seen that this is the AMX3 perovskite, and it's the hybrid perovskites where this A cation is replaced by ions like methylammonium, and when B is lead and you have iodine there or a halogen, they become sort of interesting materials for photovoltaic and other optoelectronic applications. And this is the paper that came out from Japan in 2009 that also Lingling showed. Yeah. So one of the interesting things in this class of compounds is you want to do away with the lead on the B site and maybe replace it with something like bismuth, because bismuth is much less toxic. But there is an issue in trying to replace a divalent cation. Oops, sorry, this is a divalent cation. The laser pointer and the forward button are right next to each other. You want to replace this divalent cation with a trivalent cation, and one way to do that is to alternate the divalent cation with a monovalent and a trivalent cation. So you replace a divalent M with a monovalent M and a trivalent M prime like bismuth. And it was known in this area that chlorides and bromides there are lots of them. There are very few iodides. And in fact, it was Pratap who, I think as a COVID project in Santa Barbara, sitting at home, he figured out that one reason that there are so few iodides is there aren't a lot of trivalent metal cations that are big enough to sit comfortably inside an octahedron of iodine. So there are two governing principles for forming these kinds of compounds. One is called a tolerance factor, and the other is the radius ratio. And the radius ratio with iodides for most trivalent compounds is just too small. So this could explain why there aren't so many iodides. Here's a depiction at that time of the number of double perovskite iodides that could be found. But we do want double perovskite iodides because the chlorides and the bromides have band gaps that are too large for example, photovoltaic applications. So there are trivalent cations that are large enough to form double perovskites, and these tend to be rare earths or lanthanides, to call them by the right name. So, in fact, we have the IUPAC vice president here. So they call the correct name is lanthanoid elements. So with these lanthanoid elements, like cerium 3+ and cerium 3+ and gadolinium 3+ and dysprosium 3+, we can actually stabilize these double perovskite iodides. And this was published in 2023. These are extremely air-sensitive compounds, and they're optically not particularly exciting for photovoltaic applications because the bands are very narrow, they're not dispersed, so you wouldn't have compounds that can carry charge well, and the band gaps or the optical absorption edges really are very large. And you will notice that these structures are reported at elevated temperatures. That's because these compounds are cubic at these temperatures. If you cool them down, they have the usual structural distortions that perovskite-related compounds often show, and then the crystals become quite twinned, and it's hard to do single crystal structures at room temperature. So more recently, my current student, Anya Mulligan, has made the scandium and the yttrium compound. And if you now look at the same plot of whether these compounds should be stable, according to the radius ratio and the tolerance factor, you see that the radius ratio for scandium is actually very small. So this is really a metastable compound. And in fact, there's an alternate structure that also forms in these syntheses if you're not careful. You have to trap it in this. Yttrium is just at the border of stability. But the nice thing about having scandium and yttrium is there are now no F electrons, because all the previous examples I showed you had partially filled F shells. So there are no F electrons in these compounds, and we can actually obtain band structures. So here on the left are band structures corrected, to get using something called a delta Sol correction to get the band gap right, because many of you may know that density functional theory often underestimates the band gap. Plotted alongside the band structure is the experimental optical absorption. So you see we are able to match the band experiment, and computation seem to agree quite well. Not that they need to, but they do in this case. And what you do see, though, is that these are not very dispersed bands. They're pretty flat. So these compounds are not going to make good semiconductors. If you want a good semiconductor, the bands have to sort of traverse a longer sort of range and energy. We also, in this study, were able to establish that the bismuth compound, which should form according to size considerations, actually seems to prefer an alternate structure, which I've not shown here, the so-called 3-9 structure, and density functional theory calculations suggest that the 3-9 structure is significantly stabilized over the double perovskite. So this was a quick example of some compound discovery, and we have many other examples, and you also saw a very large number of examples from Ling Ling today. In fact, this is a review that she co-authored, and there are structures, new compounds that she did when she was a graduate student, when she was a postdoc at Santa Barbara, all related to perovskite halides. So finding compounds, if you use the known rules of crystal chemistry and some imagination, finding compounds is new compounds, even in a heavily sort of studied area, is not terribly hard. So we don't yet need AI to take over our jobs. This is not to say that AI is not useful. AI is extremely useful, but we think that there is a role for the human in the loop, as they say in the AI world. So having spoken about the finding new compounds, I'm going to go to the second topic of screening compounds for materials performance. So this has been a passion of mine for many years. How do you actually quickly find the right compound for the right application instead of going through a long process of trial and error? And of course, one of the tools that we use extensively to do this is density functional theory, because density functional theory is particularly good for some applications, one of them being photovoltaics. So this was work from my former graduate student, Doug Fabini, who has been here. I should have pointed out that Anya Mulligan, whose work I showed on the double perovskites, was here last year. So Doug Fabini is one of the people who's been here about maybe 8 years ago. And what Doug did, along with an undergraduate intern at that time, Mitchell Kerner, is he went through the materials project, which has most sort of crystalline inorganic compounds, and this process here, which I won't explain in any great detail, but this process allows you to find candidate photovoltaic materials. And in fact, we think we found every plausible photovoltaic material in the materials project. Let me put it this way. From that list, we think some may be good photovoltaics, but it's unlikely that there are compounds in the materials projects that are good photovoltaics that are not in that list. Because there are some other considerations, of course. But photovoltaics are actually calculable. We know we have a strategy to using calculations to get to good photovoltaics. This is not always true for all applications. For example, here on the left is the first such thing that we ever did in my group. This is screening phosphors for solid-state lighting. And the process of having a phosphor operate where you have a partially filled F level in very dilute amounts in the inorganic host, and then you have to think about an excitation of the F electron going into a D level. These are usually europium 2+ or cerium 3+, which are F to D transitions. To do the calculation would be almost impossibly hard to get it right, even for a single compound. The idea that you could do it for a lot of compounds to screen materials is, we think, still impossible. So what we did instead was we started looking for proxies, and a proxy is something that you can calculate relatively easily that tells us about the performance. And we found in this case that a really good proxy for phosphor performance was to find a host compound into which you could put the rare earth, luminescent rare earth ion, find a host compound that had a relatively large band gap that we calculate using hybrid functionals, and a high Debye temperature, meaning we needed a very rigid host. And anyone who works with molecules is well aware that rigid molecules fluoresce more brightly than floppy molecules. So it was the same principle. So this allowed us to basically say the good phosphors live here. And again, this is actually quite extensively used now by others as well in the literature, and there are no good phosphors that don't live here, and there are no good phosphors that live here. And similarly, for magnetocalorics, these are magnetic materials that are employed for magnetic refrigeration. I actually spoke about this here. I gave a full talk on this topic some years ago. And again, the graduate student who did this work was also here some years ago. Josh Pokasley, he's a faculty in the University of Houston. And for magnetocalorics, we found an indicator based on density functional theory calculations that was related to how magnetism and structure are coupled. And it's relatively simple to calculate. And again, it's not a great correlation, but these are experimental Curie temperatures for a bunch of compounds. And the circles, the large circles, are measured magnetocalorics. And I hope you see that the higher they are on this axis, there's a greater propensity for being a large circle. It's not a great screen, but it's the only working screen out there. So I want to now talk about, following this philosophy of screening, I want to talk about finding low-K dielectric materials. And this is a relatively simple thing to be looking for. The dielectric constant, or the intrinsic capacitance that a material displays should not be a particularly difficult thing, but it turns out that there is still research to be done. This was done by Emily Morgan, former graduate student, again here a few years ago for this meeting. So why do we need low-K materials? We need them particularly for high-frequency circuits, because at high frequencies, you want both your electrical conductors to be very, very good. You want extremely low electrical resistances. And you also want your dielectric medium, the material that insulates these conductors, to have extremely low capacitance because there is something called an RC time constant. It's a product of the resistance and the capacitance. And if this number is large, then basically you cannot get fast signals through your system, right? So the dielectric that is standard, the standard dielectric that's used is silica particles encased in a small amount of polymer. And these are what go into, for example, printed circuit boards. And I can tell you that these applications are so critical that people are actually often move from copper to silver because even that improvement in conductivity makes a difference. And the copper itself should have extremely smooth surfaces, etc., or the silver, because that makes a difference. So this is how, for example, 5G circuits work. So what we were looking for was an alternate to silica that would function at 10 gigahertz, which is the temperature, which is the frequency at which we were testing the dielectric properties. And I'm trying to get us back on time a little bit, so I'll go a little fast. But there are lots of criteria. And silica, I want you to note this number, has a dielectric constant of 3.8, which is pretty low. It fulfills these criteria. So we started looking at other kinds of structures that we thought would work. And the nice thing about the dielectric constant is it can be calculated with some reliability, again with density functional theory. So this is our sort of flow chart, and this is again some of the design rules that we came out with. And we didn't actually find anywhere in the literature one set of design rules for a good material that shows low dielectric constant, particularly at high frequencies. So there is an empirical way of finding the dielectric constant developed by Shannon. It's based on the Clausius-Mazzotti equation. And Shannon has these parameters published in 1993. Shannon has these parameters, so associated with different ions are these alpha values. You can plug them in here, and the only other thing you need is the molar volume. So there's an empirical way of calculating, at least for oxides and fluorides, empirical way of calculating the dielectric constant, and there is DFT. So here is, we just selected a set of compounds that we thought are sort of maybe good candidates. The empirical value is plotted here, the DFT value is plotted here. We trust the DFT, and we see that silicates and phosphates, DFT gets pretty well, maybe with some exceptions, but borates are all over the place, and there probably are reasons for this. But when you look at this plot, you already see that 3.8 is a hard number to reach. So this is actually setting limits on how good the material that's currently used is, because this is not entirely clear to people, because people just use the first material they found. They don't necessarily spend a lot of time worrying about whether it's the best material in the world. So, so we started thinking about other possible compounds. For example, alpha-4, which is derived from silica. It's just like you derive the double perovskite from the simple perovskite. Here you take silicon 4+ and replace every silicon 4+ alternately by a phosphorus 5+ and an aluminum 3+. We thought of aluminum hypophosphate, a compound we'd worked on. There's a DFT value. And then Tony said, why not look at ALF? And you're going to hear more about ALF from his own talk day after tomorrow. It's this aluminum formate, in many ways the world's simplest MOF. And when we calculated it, it looked extremely promising. We said, wow, that's nice. That's way below silica. So we thought that's what we should work on. So we could make ALF, and Tony is going to probably tell you how it's made. And we also made the right phase of alpha-4 and confirmed the structures. And then measuring the dielectric constant at 10 gigahertz is not so easy. You have to use something called a vector network analyzer and a split post resonator. And you have to make composites of samples with paraffin wax. In fact, the traditional way of doing it is to make composites with PTFE, but we found that making composites with paraffin wax is actually much better because you don't have any porosity, and you then use this mixing law. So we calculate silica to be 3.8, and we measure 3.82, and this is showing that PTFE is messier. But when we looked at alpha-4, we calculated about 4, and we got about 3.984. So this was spot on. And the way we do this is we make mixtures with paraffin wax and we extrapolate. But ALF was a bit of a disappointment. We calculated 3.14, but we obtained 3.8, which was somewhat disappointing. And then we had to work out why that was, and it turned out that it was some very subtle structural distortion that makes a big difference. And it shouldn't, according to our additivity formula, according to the Clausius-Mazzotti equation, that modified Clausius-Mazzotti equation that I showed, it shouldn't make a difference, but it does seem to make a difference. So we now have a better calculation for ALF by allowing a structural relaxation. So this is sort of the final, the end of 1 year of work on the part of my student Emily Morgan and former postdoc Arava Zohar. But here is now the experimental measurement of the dielectric constant and compared with the DFT measurement. And we actually, I'm pleased to see that Mike Klein is going to speak about PTFE, but we did a DFT calculation on PTFE, and this is a fake PTFE. This is PTFE relaxed in the structure of polyethylene. So polyethylene has a ridiculously simple structure. It's PNMA, space group 62. For those of you who like to collect space groups, it's my favorite space group. And it only has three atoms in the unit cell, three sort of atoms in the asymmetric unit. Now, PTFE has fluorine-fluorine repulsions, which doesn't allow this kind of a eclipse structure to form, or 1,3 eclipsing. So in fact, it has these very long wavelength turns along the propagation axis. But anyway, we just stuck it in the structure and relaxed it and calculated the dielectric constant. And you see that we get very good agreement for ALPO4. We are not very far off for PTFE. We are not far off when we compare paraffin with polyethylene, but ALF was off. And again, I told you the reason. So this is the ALF that we thought we should get, and this is the DFT of the relaxed ALF, and the experiment seems to be somewhere in between. So where are we? Well, after all this, we went back to some old materials at Tony's suggestion, all silica sodalite, and in fact, this has a dielectric of 3.3. And we had initially thought of avoiding zeolites because we thought zeolites are taken water, but it turns out, Tony knew this, I didn't, that all silica zeolites don't take in water. They're in fact quite hydrophobic. So we have a patent being filed on this. We've not actually published this, but we think that any all silica material which is rigid and has small cages, small pore openings, is a good candidate. So with that, at least I've told you a little bit about compound discovery and how we think it's often distinct from materials discovery, because the material should have a function. And in the case of, I showed you some screens, but in the case of locate materials, I've shown you that we can actually calculate it, and then we can just guess what could be a good material, do the calculation, and make it. So that's my last slide. So with that, thanks again to the host.